Good morning. I would like to start the second session this morning. My name is Jürgen Smet. I'm from the Max Planck Institute of Solid State Research in Stuttgart, and it's a pleasure to chair this session. The first speaker of this session will be Klaus Ensslin, and he will discuss coherent electrons and rings.
Okay, I would first like to thank the organizers for inviting me to this very special conference. I will try to cover a little bit the basics of electron interference in mesoscopic devices. I will first show you something about electrons and rings in general, how we can prepare them and measure them. Then I will show a little twist on the Aharonov-Bohm effect by including spin-orbit interactions. And then at the end, I will show you a series of experiments that deal with the handling of individual electrons in these nanostructures, so you can really monitor transport of individual charges in a time-resolved fashion. My collaborators are Simon Gustafsson, Ivan Chorobalko, Theo Choi, Boris Grivich, François Molitor, and Thomasin. So let me start out with a little movie. What you saw here was the surface of a ring structure. Now we are flying through a ring potential landscape. And this should tell you a little bit how we torture our electrons to really make them interfere and see a Aharonov-Bohm effect. So it's getting a little chaotic now. We are flying along one of the arms of this ring here. You see that's the ring structure in the semiconductor. The ring structure in this case has 4 terminals, and this is the final sample. So you will see a lot of sort of potential profile pictures in my talk. These pictures, as this one here, are actually made with an atomic force microscope, and they are really the topological profile of a semiconductor structure, but they pretty much resemble the potential landscape that the electrons feel while the electrons actually reside below the surface of the semiconductor. So let me start out with a typical trace here. This is one of the newer materials. This is a graphene sample. This entire sample has been cut out from a layer of graphene. You see the dark areas. This is where the graphene has been removed. The gray areas, this is where the single layer graphene is still intact. You see this is a 4-terminal geometry. You can pass the current in this direction, measure the resistance, and you can measure very nice Aharonov-Bohm oscillations. So that's the resistance of this device as a function of magnetic field. I'm sorry, the B here disappeared. And you can do a 2-terminal, a 4-terminal experiment, and the amplitude of these oscillations is of the order of 10%. So it's as good a mesoscopic device as gallium arsenide and many other samples where the Aharonov-Bohm effect has been observed. I should mention here that you see these side gate structures, which are cut out of the same graphene flake. And so with this technology, you can make very intricate samples that allow you to make phase-coherent electron physics. And I think the nice thing about the future of graphene is probably that you can make things very, very small, because you're really talking about one monolayer of atoms. You can make things very small, and in the end, you're only limited by the technology in your lab, which is very different from semiconductors, where electrons are typically below the surface, and so you can make things only as small as the depth below the surface, and that's a technological limitation. Okay, let me just compare the typical mesoscopic rings to other rings that we have. I think sort of the smallest ring that we have is a benzene ring, 0.5 nanometer or so diameter, and here is the left. That's the predecessor of the LHC. And I just wanted to flash this here if you look at the orders of magnitude in difference in length scale. And now if you apply a simple Aharonov-Bohm argument to these 2 ring structures, and you ask yourself, how many Tesla do I need to add 1 flux quantum through the system? Then you see for the benzene ring, a flux quantum corresponds to roughly 5,000 Tesla. So this will be a very tough experiment to be done. And you also see that for the lab, this is of course a super tiny magnetic field. And of course, one also has to ask the question about the coherence of the electrons in this ring. So the message of this picture is that if you go to mesoscopic structures that live on the length scale of 100 nanometers or so, we are very fortunate that the magnetic field that corresponds to 1 flux quantum roughly corresponds to 100 millitesla or 1 Tesla, which is something which is easily accessible in the lab. So these are very nice length scales to actually do the Aharonov-Bohm experiment with tools that we have available. Now let me give this a little twist, and let's look at a sample that is not just a free electron gas, but is a free electron gas with some amount of spin-orbit interaction. So in other words, when the electron wave function goes around the 2 arms of the ring, and we add this spin-orbit interaction, the spin direction is coupled to the orbital propagation of the electron, And this is what is also called, it's a special case of Berry's phase. And the idea is that the Aharonov-Bohm effect is modified. So it's not just the old Aharonov-Bohm periodicity for the free electron, but you add this interference term that comes from the precession of the spins in the spin-orbit field, and that gives rise to a lot of predictions. The literature is full of theory predictions, and there are 4 experiments in the literature so far. So this is the history of the field, the different materials. This, for example, is electrons in indium arsenide. Indium arsenide is a material that provides very strong spin-orbit interaction in the conduction band. This is holes in gallium arsenide, and we will come back to that. Holes generally have a much stronger spin-orbit field than electrons. Here is another example in a 2,6 semiconductor, and here is an example in an indium gallium arsenide sample. And the basic feature that you would like to look for is if you simply have electrons, you expect one nice Aharonov-Bohm periodicity. If, however, you include the spin and spin-orbit interactions, you expect that there might be a splitting of the Aharonov-Bohm oscillations or a splitting in the Fourier transform of the system. Now here is an example, and this particular material is p-type gallium arsenide, so it's very similar to the high mobility electron gases, except it's p-doped instead of n-doped. The mobilities are so high that these samples are good enough for fractional quantum Hall experiments, and you see here the raw data. So this is the sample. The black area is where the electrons may reside. The white areas represent barriers, so the electrons can come from the left, then the wave function may penetrate this ring-like area and then exit to the right. The raw data is the blue data. If you subtract the red background, and the red background has a classical origin because of the geometry of the sample, you get this black trace down here, and you see there's very highly reproducible Aharonov-Bohm oscillations. You see the pattern is even as a function of magnetic field, which is because of time reversal invariance. And you also see that they're beating patterns. It's not just one Aharonov-Bohm signal, but you can really see by eye that there's a beating pattern in these Aharonov-Bohm oscillations. You can take this data and blow it up a little more in this interesting region around the first node, and you see there's really a phase change. If you see the minima here lie exactly at the boundaries of where you add one flux quantum through your ring. So this is this area down here, shaded area, and exactly at the node you have this phase change by pi. And you obtain the same thing if you go to negative magnetic fields. So it's a very clear indication that you have 2 different components that play a role in this Aharonov-Bohm effect. If you take a Fourier transform, you get a splitting of your Fourier peak, and you can even have a double peak, but one should always be very careful with looking at splittings of Fourier transforms if you don't see the feature itself already by eye in the bare trace, because Fourier transforms can often give you a lot of splittings depending on how you choose the intervals of the Fourier transform. Now the important thing is that this should also occur for higher harmonics. And this is an example here. This is now taking the same data but looking at the h/2 oscillation, whose amplitude is typically more than an order of magnitude lower than the h/e oscillations. So they correspond to the situation where the wave function goes around twice along the perimeter of the ring. Here's again the raw data. You subtract the background, you get very nice oscillations. These are the h/2 oscillations extracted from the raw data, and you see they're beating-like features in the h/2e oscillations. They're not as clean as in the h/e case, and the reason is simply the experimental resolution, because it's only a tiny part of the total resistance signal that oscillates with that frequency. But again, you can calculate these beatings here, and you can compare to what you expect, assuming the spin-orbit splitting, which is known in p-type gallium arsenide. So this is a very interesting quiz of using the Aharonov-Bohm effect to learn something about spin-orbit interactions. Now, let me change gear and tell you a little bit about time-resolved experiments. Time-resolved in the sense that we can really monitor individual electrons as they pass through these nanostructures. And I want to start out by a very nice and pioneering experiment by Tonomura and company. Basically what they did is they used electrons in an electron microscope, and they diluted the electron beam to such an extent that the electron that left the source had the possibility to go to a double slit and then landed on the screen. And before the next electron was released, the first electron had to be on the screen to make sure that there's only one electron in the system at a given point of time. So you make sure that the electron really interferes with itself and there are no other electrons around that could contribute to the signal. Now, it would be very nice to do a similar experiment in solid-state physics, but in solid-state physics the problem is the observation screen, because typically you can measure some intensity of electrons, but you cannot have many different sources or many different detectors at the same time. So what is the solution? The solution is the Aharonov-Bohm effect. This is the schematic of our setup. So we have a source of electrons, we have a drain, and then we provide two possible passes for these electrons emanating from the source. These are two quantum dots, and then we have a special tool that allows us to monitor the flow of these electrons through the device. So this is how the real device looks like. Again, the yellow barriers represent the potential hills for the electrons. So the electron may come from the source contact. It tunnels into this, through this first tunnel barrier to the first quantum dot. And then you see there's this little pillar here in the center which opens a hole where no electron gas is left. And then there are two possibilities to tunnel from quantum dot 1 to quantum dot 2. That's the interfering path. And then the electron may tunnel out from dot 2 out to the drain. So the important feature here is now that as we apply a magnetic field, we change the relative phase of these two paths. And as we monitor the current through this device as a function of magnetic field, we expect this B-periodic pattern of the Aharonov-Bohm effect. Now there's a little gadget up here, and this is our detector. And this detector is simply a tunnel barrier, and the conductance of this tunnel barrier is coupled to its environment by electrostatic means. So each time you load an additional electron into your system here, there's capacitive crosstalk to the other side, which leads to a conductance change of our detector. And if we monitor this conductance change as a function of time, we can really probe how the electrons go through the entire structure as a function of time. And that's important because we're looking at very slow electrons or a very small rate of electron transfer, something like 1 electron per millisecond. If you convert this to a current, this corresponds to a current which is about 4 orders of magnitude smaller than any IV amplifier can measure. So this is also a way of measuring very, very small currents of the order of attoamps, 10 to the minus 18 amps. So the idea is now the following. We know the classical electron takes the lower path, or it takes the upper path. And of course, the quantum electron is supposed to take both passes at the same time. So let me show you the data. This is the count of our detector, the count rate. Horizontally, you see the magnetic field. And if you listen, you can maybe hear the sound on my laptop. So we're really listening to individual electrons on a semiconductor chip in the lab. And you see very nicely how this Aharonov-Bohm pattern here builds up as a function of magnetic field. And down here, you see a typical trace measured at one of those magnetic fields. So this is our detector current. The detector current fluctuates between two values. The two values correspond to electron in, out of the double dot device. And if you simply count the downturns, each downturn means one electron has been effectively transported through the double dot device. This gives you a count rate, which is the vertical axis here. And you see very nicely that you can do an experiment pretty much in the same way as you can do it for individual electrons in vacuum. Now, if you look at this, it's actually quite an amazing experiment because it means that the electron that has traveled something like 100 nanometers, it has passed something like 1 million other electrons in the system on its way. Because this is a solid state device, it consists of many atoms and electrons. And the important feature is that all the million other electrons, they are in strongly localized states. We have control over the quantum state of one individual electron by these gate electrodes, and we can monitor the flow of this electron with this detector, which has single electron resolution. And that gives rise to this trace. So if you just take the envelope of this trace, it looks something like that. That's the Aharonov-Bohm pattern. And now if you look at that, again, there's something quite amazing, is that the visibility of this signal is almost 100%. Which means that basically all of the electrons that we detect here are phase coherent. And that's again something unusual in solid-state physics because in a solid you have a Fermi sea of electrons. The electrons talk to each other. You heard by Joe Imrie there is dephasing by the electrons. And typically these degrees of freedom lead to the fact that the amplitude of the Aharonov-Bohm signal goes down. And at low temperatures, if you have 10 or 20% amplitude, you're doing pretty well. Here it's almost 100%. Now, this is not surprising for this particular arrangement because the electron is actually tunneling through the device in a very fast way, probably faster than picoseconds. And on this time scale, there's simply no time to couple to the other degrees of freedom in the system. And that's the reason why decoherence is extremely weak here. Now, to check this, you can do a very simple experiment. You can increase the temperature. This data is taken at something like 100 millikelvin. If you increase the temperature for a solid-state device, you broaden the distribution of your electrons in your leads, and that typically gives rise to stronger decoherence, and the Aharonov-Bohm signal goes down. Now, if we increase the temperature here, these are traces taken for different temperatures, and you see nothing is happening as you go up to 400 millikelvin. And the reason that nothing is happening is the same as I told you before. The electron is actually tunneling through a state, which is a very fast process. It doesn't care about the electrons in the leads, which are thermally broadened, and therefore the temperature does not give rise to decoherence. As you go to even higher temperatures, like 500 millikelvin or even higher, then KT becomes comparable to the internal excitations of the system, which means that you offer additional possibilities to go through your system, not only through the ground state, but through the excited state. The excited state will have a different phase, and therefore the different Aharonov-Bohm oscillations will average out. So the fact that the oscillations stay out here is not due to decoherence, but it's actually due to averaging of different Aharonov-Bohm signals. Okay, now if you have such a system, the Aharonov-Bohm effect is a very nice tool to measure interference, but it's also a very nice tool to learn something about the measurement process in the quantum system itself. That's the sample again that I've shown you, electrons coming from here, dot number 2, dot number 1, and then leaving out to the drain contact, and here's our little detector. So the fact that we are actually detecting these electrons on an individual basis, does it change the measurement outcome of our system? And in order to answer this question, we have to think a little more about this detector down here. And the detector is nothing else than a tunnel barrier, as I told you. It's a tunnel barrier whose conductance is a very steep function of the environment, or in particular, of the charge state of this neighboring system here on the left. So how can we think of this tunnel barrier or this detector to influence our measurement system, our measured system? This is a characteristic or schematic of the tunneling barrier. So electrons come from the left, and then as we know, they have a certain probability of being transmitted or reflected. So if you have a noiseless incoming stream of electrons from the left after the tunnel barrier, you will have a partition stream of electrons because of this probability distribution. So you have fluctuating charges over here. You will also have a reflected beam of electrons, and they also fluctuate in space. So if you have fluctuating charge in space and they propagate, it corresponds to fluctuating charge in time, and that is nothing else than a fluctuating electromagnetic field, and we can call this photons. So basically the fact that the electrons are scattered here by these tunnel barriers leads to the emission of an electromagnetic spectrum. And this is the spectrum as it has been calculated by many people, and in particular by Aguado and Covenhoven. So T is the transmission probability of the barrier, V is the voltage applied across the barrier, omega is the frequency of the emitted photon, and down here is the temperature dependence. So basically what this tells us is that the electron that comes from the left and is transmitted, it can emit photons. The maximum energy of the emitted photon is given by the voltage applied across the tunnel barrier, and the spectrum itself is given by this equation here. So this is now the picture that we have. We're looking now at a double dot system. You see these are the source and drain Fermi levels. Here's dot number 1, here's dot number 2. We are looking at a system which is off resonance, so no electron transport, just by an applied bias across the system. This electron is trapped down here. It cannot escape to source and drain. This excited state is too far away to be accessible by KT. So now we have our little detector here. The detector emits a photon. The photon hits the electron in the ground state. The electron goes to the excited state. It may leave the system and is replaced by an electron from the right drain contact. So basically, by exciting this electron by a single photon, we have effectively transported one electron from right to left. And this we can count again with our detector, because our detector has single electron accuracy. So the detector has two functions. It first drives the process, and then it actually measures that the electron transfer has really taken place. So let's see whether we can see that in the experiment. So what you see here is a color scale plot, and the color scale plot is simply the color scale for the count signal. So the more color we have, the more electrons per second. So if it's dark here, dark black means no electrons traverse the system. Then you see two axes here. The first, the horizontal axis, is the detuning. That's the energy difference between the two levels in the dot. So basically, large detuning means we need a large photon energy to go from the ground state to the excited state. But as we go to zero detuning, we know this is a coupled double dot system. So this gives to a tunnel splitting between the two states, and the minimum tunnel splitting is exactly given by this energy scale here. So this is our detector, if you want. This is the energy scale for the photon that we need, and the vertical axis is our emitter. That's the bias applied across our tunnel barrier, and this determines the maximum photon energy in the system. So now what you see is there's a finite gap here, that's the tunnel splitting, and the minimum photon energy that you need to come across this gap is exactly this energy here. Now as you hit this energy, you can get more events in your system, more counts, more electrons being transferred, because you have more photons with the right energy that can give rise to this process. So the blue dashed line is simply calculated by the simple quantum mechanical model, where T is the tunnel splitting, which is known from other experiments, and delta is the difference in the level separation between the right and the left quantum dot. So this omega here is the blue dashed line. It's known from other experiments, and you can very nicely explain the data over here with the simple model. You can also quantitatively understand how the count rate increases as you increase the bias voltage across the tunnel barrier. So the system looks now a little bit like this. Here's our double dot system. Here's our little detector. The detector is driven. It emits a photon that drives the electron from left to right, which gives rise to electrostatic coupling to the detector, and the detector again monitors what has been going on. So if you lean back a little bit and look at the system in more general terms, it could look something like that. In quantum optics, we know that the size of an atom, about a nanometer or so, is much smaller than the wavelength of the light that is absorbed by the atom. Now in our case, it's even more extreme. Our artificial atom, or our quantum system, is more something like 100 nanometers. The wavelength of the photon that corresponds to the energy scale that I've just shown to you is in the microwave range, and so it's something like 10 millimeters. It's a macroscopic object, this photon. So now you can ask the question, is it really a photon? Because you see here, the distance between the emitter and the detector is really on chip. Everything happens on the scale of something like 100 nanometers. And the exchange of energy occurs via electromagnetic radiation. And so we're talking here about the absolute near field of this electromagnetic process. So there's never a freely propagating photon in our system, but these are two systems, two quantum systems, that exchange their energy by electromagnetic fields in a quantized fashion. Now once you accept this picture, you can of course dream about more complex systems, pretty much in the spirit of quantum optics, that you say, okay, if we have one quantum system that emits radiation, this radiation should consist of anti-bunched photons. There shouldn't be two photons at a given energy at the same time. So you could build two detectors. You could do something like photon anti-bunching experiments on a chip. And you can do more complex things by adding more detectors and more dot systems. And this is something that is going on in the lab, and it's, as you can imagine, quite challenging technologically. So let me conclude here. Let me thank my collaborators, and let me thank you for your attention.
Now for discussion.
With the double slit with a, you mean a real double slit?
Double slit experiment for an electron, where you put your detector on either side of the slit.
Okay, so our version of the double slit is the ring and the Aharonov-Bohm effect. If you do a real double slit experiment, then you have freely propagating carriers. And they typically travel very fast. They travel with the Fermi velocity in the system. And our detector is not sensitive enough to detect an electron that passes by with 1/100th of the speed of light. That's why we have to trap our electron in a quantum dot, then it sits there, and then our detector can measure it. So it's a question of the sensitivity of the detector.
The detector doesn't tell which side, you know, like, otherwise it would destroy the interference.
Yes, that's of course a very good question. So as you say, the detector is of course placed asymmetrically with respect to the lower and the upper path. In the end, it's a matter of time constants. As I told you, they elected 3 time constants for tunneling. Tunneling in, tunneling from left to right, and tunneling out. The tunneling in and tunneling out we can control by these tunnel barriers, and we tune it to the scale of kilohertz, so 1 electron per millisecond, because this is the bandwidth of our detector. Our detector is relatively slow. Now the process itself from left to right is relatively fast. It's gigahertz. So in other words, the time scales are very different, and therefore this detector has no which path information. But of course, one of the things that we would like to do and that we're working on is to increase the bandwidth of the detector to approach the tunnel traversal time.
Back to the first part of your talk, the beats in the Aharonov-Bohm oscillation. Such beats also arise because the channels on the two sides of the ring have a finite width, and therefore electrons can surround different fluxes. Have you excluded that possibility?
Okay, so this is a question from the specialist, and of course, this is a very valid question. So I should say that I told you there are 4 experiments in the literature with ours. There are now 5 experiments in the literature, and none of these experiments has completely excluded the possibility that you just mentioned. So, and in experiment, it is very hard to exclude, because in the experiment, at least with the present samples, we cannot make a single mode ring which would exclude that possibility. So we have a multi-mode ring. So the arguments that we put forward right now are just a lot of plausibility arguments. One of the arguments is the position of the beat, but then of course you can come back to being related to some other feature. And we think that in particular with the h/2e oscillations, there's also a position of the beat. You can relate the position of the beat in h/2e and h/e and relate it to the strength of spin-orbit interaction. But it's just a series of arguments, and I agree with you that experimentally we cannot completely rule out the other pretty much simple effect.
Well, if you look at the tunneling of a wave packet through a barrier, then you find that the tunneling time is 0. So how do you come up with your tunneling time then?
Okay, so I didn't tell you that I measure a tunneling time. What I measure is a rate how electrons arrive. I don't measure how fast they tunnel, because I think this would be much more exciting than what I told you here. So, and because the detector is, as I told you, kilohertz, we have no chance of ever hitting that regime.
The question to the last part. If you change your detuning parameter from negative to positive value, then your current for the detector will change from one value to the other value continuously. In equilibrium, I would expect that it should be just a smooth tangent, hyperbolic tangent function. But out of equilibrium, it should probably change. Did you try to measure this?
It's another very good question. So if you basically go through zero bias, then you're limited by thermal excitations. So you have thermal tunneling. Now the question is, if you want to go to the linear regime or nonlinear regime, you have to apply an even larger bias voltage. Now, for the system that we're looking at here, it's again related to the bandwidth of the detector. We can only measure small currents. If you want to go to the nonlinear regime, you need large currents. And that's not possible with this method here. So you need to go back to conventional noise experiments.
One more question.
Okay. So coming back to the question that Amnon asked, by the resistance, can you estimate the number of transverse mode in each arm of the ring?
It's about 3. Yes. So it's more than 1 and less than 10.